All right, so we're diving into Huffman coding and data compression today, which, I mean, wow, it's like every time you send a text or, share a photo online, it's kind of wild to think about all the clever stuff happening behind the scenes just to, like, make those bits and bytes travel efficiently. And that's what we're going to unpack, right? Like, how does this Huffman coding magic actually work? And all thanks to the articles and notes you sent my way. Looks like we've got a good amount of material to dig into. But maybe, like, before we get lost in the trees, so to speak, could you just give us the high level view of data compression itself? Like, why do we even need it in the first place?
Yeah, sure, totally. Data compression, it's all about, I guess, shrinking things down, digitally speaking,
Yeah.
like finding clever ways to say the same thing, but using fewer bits. Those zeros and ones that computers love.
Okay, so fewer bits, less space. Makes sense. But how does it actually, happen?
Well, one way to think about it is, your fundamentals of programming notes. They talk about ASCII in coding. And like, for instance, if you wanted to store the phrase more free coffee in ASCII.
Or free coffee. Yeah, essential stuff.
Right. Well, each letter, each space even, takes up 8 bits. So that whole phrase ends up being like 112 bits long.
112 just for more free coffee. Yikes.
Yeah, it kind of adds up. And that's where the idea of variable length encoding comes in, right? Like instead of every character being the same 8-bit chunk, we could maybe make some characters like, shorter if they're used more often.
Ah, so it's like giving priority to the popular letters, kind of like a VIP line for the characters we use all the time.
Exactly. And the example they give using a specific variable length code, that same more free coffee can be squished down to just 34 bits.
Wow, 34, that's way better. But wait, if we're suddenly making codes different lengths, like how does the computer know where one character ends and the next one begins? It seems like things could get pretty jumbled up fast.
Yeah, that's where the whole prefix free thing comes in. That's super important. It means like no code for a character can be the beginning of the code for another character.
Oh, I see. So there's no overlap, no chance of accidentally reading like part of one code is a different one.
Mm-hmm.
Clever. But how do we actually create these codes?
Well, that's where Huffman Coding steps in. Both the Medium article and the Program Is notes talk about that they're good resources to get started with.
Developed by this David Huffman guy, right? Back in the 50s. Pretty amazing that something from that long ago is still so relevant today.
So what's the core idea behind Huffman Coding? How does it actually, crunch those bits down?
So the central concept is this. You look at how often each character appears in the data, like how many E's compared to X's, and then you give the frequent ones shorter codes and the rare ones, well, they get the longer ones. It's all about leveraging those frequency patterns.
Okay, so it's really all about statistics, huh?
Yeah.
Makes sense. I guess the more uneven those frequencies are, the more you can squeeze things down. Yeah, exactly. And to figure all this out, you use this thing called a Huffman tree.
Okay, I gotta admit, trees aren't exactly my forte. What's the deal with these Huffman trees?
Well, think of it like a family tree for data, right? You've got your ancestors at the top, the root, and then as you go down the branches, you get to the individual members, the characters in this case. And the most frequent characters, well, they're like the closest relatives, the ones with the shortest path from the top. More technically, each point on the tree is called a node. Some nodes have children, that's how we build the connections. And the characters themselves. They're the leaf nodes, the ones at the very ends of the branches.
Right, so the characters are like the leaves. Makes sense. But how do you actually construct this whole family tree from, a bunch of data?
So the notes in the articles break it down into a few key steps. First, you just got to count how often each character appears. Like in that Medium article, they use A, B, C, B, A, C, D as an example.
Yeah, I saw that.
So like A shows up 3 times, B twice, C twice, and D just the once.
Frequencies, check. And then what?
Then you create a leaf node for each character, like A, B, C, D. And each node gets its frequency as like its weight. Then the fun begins.
Yeah.
You pick the 2 nodes with the smallest frequencies. They're going to be buddies now.
Like the least popular kids at the party, they got to stick together.
Huh, exactly. And you make a new node, their parent, and its frequency is just the sum of the 2 you combined.
So the example, that would be D in either B or C, right? Since they're both at 2.
Yeah, you got it. And you keep doing this, combining nodes, always picking the 2 with the lowest frequencies until you're left with just one node at the very top. That's your root, the grandparent of all the characters.
So it's like a bottom-up building process, starting with the individual letters and their counts, and then merging until you get to the big boss at the top.
That's it. And your programming notes mention using a priority queue for this, which Sounds kind of fancy.
Priority queue, is that like, I don't know, a line where you get to cut in front if you're more important?
Kind of, yeah. It's like a special list where the elements are ordered based on their priority. So in this case, the nodes with the lowest frequencies, or the VIPs, they get processed first. Makes the whole combining thing much more efficient.
So it's not just about the frequencies themselves, it's also about making sure you're always grabbing the right nodes at the right time. Okay, we've built our tree, we've got all these nodes connected. Now, how do we go from that to the actual codes, those EOs and ones?
Right, so now it's time to walk the tree. You start at the root, and to get the code for a character, you basically trace the path down to its leaf node. And as you go, you assign a 0, 1 if you go left, and a 1 if you go right.
Oh, so it's like left turn 0, right turn 1.
Exactly.
Yeah.
And the sequence of those turns, that becomes the Huffman code for that character. So in that ABCBACD example, the Medium article shows that A ends up being just 0, B is 10, C is 111, and D is 110.
So the more frequent ones, like A, end up with shorter, more direct paths, just like we said. Now I'm remembering that prefix-free thing. How does this tree structure actually guarantee that we get those special codes?
That's the beauty of it. Remember how the characters are always at the leaf nodes, right?
Yeah.
Like the endpoints? So the codes, those paths, they only stop when you hit a leaf. That means no code can ever be part of another code because you're always stopping at a character.
So it's like if you reach a leaf, you're done. You can't go any further down that branch.
Yeah. It completely avoids the confusion of like 101 meaning one thing or maybe something else entirely.
Yeah.
The BBC Bite-Size Notes had that example, remember?
Yeah, 101 meaning either B, C, or T. That would be a mess. So the tree structure itself just like solves that problem.
Yeah.
And your programming notes, they mention some code stuff like functions called build htree and htree to hcode.
Yeah, those are just like the technical names for the steps we've been talking about. So the build htree one, that's what takes the frequency data and uses that priority queue magic to create the tree. And then htree toast code. Well, that's the one that walks the tree and creates the actual codes, like that lookup table of character to its bit sequence.
So one builds the map, the other one reads the map. Okay, that makes sense. But what about going the other way? If we have an encoded message, how do we decode it?
It's like retracing your steps. You start at the root of the tree again, and you read the encoded bits one by one. A 0 means you go left, a 1 means you go right. Keep going until you hit a leaf node, and boom, that's your character. Then you go back to the root and do it again for the next bit.
So it's like using the map to navigate back to the original destinations.
That's it. But the decoder needs the same map, right? It needs the Huffman tree, or at least the code table, to know what those 0s and 1s actually mean.
Yeah, makes sense. If you don't know the code, it's just gibberish. But this makes me wonder, like, if this Huffman coding is so great at saving space, why do we even bother with, things like ASCII? Why not just use Huffman coding for everything?
That's a good question, and it points to the trade-offs, right? Huffman's great when you have those uneven frequencies, but ASCII, even though it's fixed length and might take up more space overall, it has its own perks.
What kind of perks?
Well, with ASCII, since every character is 8 bits, it's super easy to know where one ends and the next one starts.
Yeah.
You don't have to do any fancy tree traversal. Plus, ASCII is like the universal language computers speak. Everyone agrees on it, so you don't have to send extra information about the encoding itself.
Right, so ASCII is like the default, the common ground. It's not always the most efficient, but it's simple and everyone gets it.
Exactly. And in reality, like your notes mentioned, a lot of actual compression algorithms, they combine different approaches, like deflate, used in Zibi files. It uses Huffman coding, but also this LZ77 thing.
So it's like playing to each method's strengths.
Yeah, exactly. And there are other cool techniques, too, like arithmetic encoding, LZ7778, a whole rabbit hole to go down there.
Yeah.
But it shows that Huffman's just one piece of the puzzle.
And speaking of puzzles, those notes mention this really cool application of Huffman coding for, like, accessibility. Can you talk a bit about that?
Right. Yeah, it's pretty neat. The idea is, if you think about people using those linear scanning interfaces, for typing when they might have motor impairments, well, by putting the most frequent characters earlier in the scan sequence, you're essentially applying the Huffman logic to make typing faster and easier.
Wow. So it's not just about saving storage space. It can actually have a direct impact on how people interact with technology. That's awesome. And of course, Huffman coding is like everywhere, right? And ZIP files and faxes and even JPEGs and MP3s, like how we listen to music.
Yeah, it's everywhere. The whole idea of using prefix codes efficiently, Well, that pops up all over the place,
Mm.
especially when you're trying to save bandwidth or storage, like that Dremio article pointed out.
Yeah. But it's not like a perfect solution, right? It has its limitations. I think the Dremio article mentioned some of those.
Yeah, like we said, if all the characters are equally likely, Huffman coding doesn't really do much. And sometimes it might even make things slightly bigger because you have to include the tree itself. And some of the other articles, like the Programmas and Kunal Jain ones, they talk about how the encoding process itself can take some time, especially with massive amounts of data.
Right. So there's always a balance, right, between how much you can compress and how much effort it takes to do it.
Exactly.
Okay, so I think we've covered a lot of ground here. Thanks to your notes and all these articles, we've gone on quite a journey through Huffman coding. And the big takeaway, I think, is that this seemingly simple idea, just analyzing how often things appear, has led to this incredibly powerful technique that's used all over the digital world.
Absolutely. It's a testament to the power of understanding patterns in data.
It really makes you appreciate the ingenuity behind it all, like all those billions of bits flying around. And thanks to Huffman coding and other clever techniques, they're doing it way more efficiently than they otherwise would. And who knows what the future holds? Like, as we generate more and more data, are there even more efficient ways to compress it? It's pretty exciting to think about.
It definitely is. The possibilities are, well, pretty much limitless.
Yeah, exactly. So that wraps up our deep dive into Huffman coding and data compression. Huge thanks to you for bringing these fascinating materials to our attention.
You're welcome. It's been a great discussion.
And to all our listeners out there, if you enjoyed this exploration of the hidden world of bits and bytes, please do us a favor and like, share, and subscribe to the All Sorts podcast on YouTube. It really helps us keep the deep dives coming. And hey, if you're curious about other topics, other mysteries of the universe we haven't tackled yet, let us know. We're always looking for new ideas. And don't forget to follow the All Sorts podcast on X, Instagram, and Threads for more behind-the-scenes fun. Until next time, keep exploring,